Assalamu alaikum and a very good day to everyone. Today we're going to learn about fluid therapy in children. The objective of this lecture will be divided into three parts. The first one is talking about fluid compartments. Number two, we will talk about fluid and electrolytes. And number three, we're going to talk about, in general, fluid in children. At the end of this lecture, you should be able to understand the physiology of fluid in the body. You should know the important electrolytes and its clinical application. You should be able to prescribe fluid in children, and you should know the basic nutritional requirement in children. When we talk about fluid therapy, it is actually a drug, a kind of medication that we prescribe to our patients. But the problem is, up to now, we still don't know the dose. Whatever that we prescribe for our patients in the ward, especially in children, are mainly from extrapolated graphs or information that we gather from normal children. Although we do not know the dose exactly for children, but we do know a few things for a fact that fluid stays in different compartments in our body, and fluid homeostasis involves shifting of fluid in the different compartments. And we know that the capillary Starling's law has been revised, and we should know the concept of osmolarity and tonicity because this is the basis of fluid therapy. Now, we know that our body is mainly made from water, but how come we do not see ourselves like a bag of water or even a ball of water rolling around? And in fact, we hardly can see water inside our body. How is that so? So if you look at this picture, it is shown A, B, and C, and the water actually resides in different compartments in your body. So A being the intravascular compartment, B being the interstitium, and C is the intracellular compartment. This graph should be very familiar to you. So 60% of our body weight is actually made from water, and 2/3 of that 60% is actually in the intracellular fluid, means it's inside the cell. And about another third of the water in our body is divided into interstitium and plasma volume, which makes up the extracellular fluid compartment. And what you need to know that is important is that the third space is the interstitium. And we always say that, patients losing fluid into the third space. So the third space are the area where it can collect fluid in the pleural cavity, in the synovium, as well as vitreous of the eye. This graph is showing how the intercompartment interacts with each other from plasma to interstitium to intracellular fluid. And you can see here how the fluid in plasma is being maintained by the intake as well as the output. And in between the plasma and the interstitium, there's capillary membrane, which lies the capillary Starling's law. And you can see here the water from the interstitial fluid is kept replenishing to the plasma via the lymphatics. And in between the interstitial fluid and the intracellular fluid, you have the cell membrane that water shifts via osmotic gradient. So what makes water move? There are three things in general: the osmolarity, the serum sodium, and the oncotic pressure. And that brings us to the concept of osmolarity and tonicity. Osmolarity is 2 times sodium plus potassium plus urea and plus glucose, which gives us 285 to 295 milliosmol per liter. Osmolarity is measured when you calculate all solutes, which are the sodium, potassium, urea, and glucose. But tonicity is when you calculate the same solute with a semi-permeable membrane in between the two compartments. Is that what you're seeing? The endothelium separating the intravascular compartment and the interstitium. Tonicity measures the solutes that can't cross over the endothelium easily and what stays in the intravascular compartment. That is why tonicity of the fluid that you prescribe is important, because it determines whether water remains or start moving out from intravascular compartment. Remember, the intravascular compartment, although is the smallest compartment in your body, it is the one who generates cardiac output. Let's have a look at the different types of fluid that we often use. The normal saline consists of sodium 150 millimole per liter and chloride 150 millimole per liter, which gives us serum osmolarity of 308 milliosmolarity per liter. If you times it to the coefficient for the plasma, which is 0.93, the osmolarity for normal saline is actually 286 milliosmol per liter. So that is why it's called isoosmolar, as it is similar to the serum osmolar in your body. And the fact that the sodium doesn't cross semi-permeable membrane easily in between the intravascular and interstitium, the water remains in the intravascular. Therefore, it is called isotonic. What about the half saline D5? If you look at the osmolarity, it's actually 430 milliosmolarity per liter. This is why it's called hyperosmolar fluid. But as you know, this is mainly contributed by the dextrose and not the sodium. The sodium concentration is very low. It's only 77 millimole per liter, much less than the serum sodium in the intravascular compartment, which is around 135 to 145 millimole per liter. And dextrose is a form of carbohydrate, and it will be metabolized in the body. Therefore, the only solute that stays in the intravascular is sodium. So with the very low sodium, this will actually mix up the serum osmolarity of only 154 milliosmolarity per liter. That is why it is called hypotonic solution. Since serum sodium is very important to be maintained in the intravascular, use fluid that is isotonic in order to keep water in the intravascular space to generate good cardiac output. All the fluid that I mentioned just now was crystalloids. Another type of crystalloid is called balanced solution. A good example is Ringer's lactate or Hartmann solution. This is because it contains other electrolytes apart from just sodium and chloride, mimicking the plasma electrolytes concentration. One of the latest examples of balanced solution is sterofandin. You can see in this table the different types of crystalloids and its composition. But we do know a few things for a fact that fluid stays in different compartments in our body. You can see in this table the different types of crystalloids and its composition. Another important type of fluid that we commonly easily available. Another important type of fluid that we commonly use is colloid. Some examples are gelafandin or Voluven. The main differences between crystalloid and colloid are: number 1, crystalloids are easily available and much cheaper. Number 2, colloids stays 4 times longer in the intravascular compartment as compared to crystalloid. And number 3, colloid has risk for allergic reaction. Another important type of fluid that we commonly use is colloid. This graph shows where would the fluid be distributed once we administer it intravenously. For dextrose-containing solution, it will generally be distributed into the intracellular compartment. It makes sense, right? Because that is where the cells will be doing most of the metabolism. The normal saline and balanced crystalloids will be mainly distributed in the plasma as well as the interstitium, and colloid or blood products will mainly remain in the intravascular compartment. And we know that the capillary Starling's law has been revised, and we should know. Let's talk about the capillary Starling's law. As we all know, the fluid will be moving from the arterial end of capillary into the interstitium and back via the venule end of the capillary. This is all by virtue of the changes in the hydrostatic pressure and oncotic pressure between the intravascular compartment, which is the capillary, and the interstitium. However, there is now another layer that maintains water in the intravascular compartment, which is the glycocalyx layer. And with this, there is a new theory of revised capillary Starling's law, whereby the fluid will be moving from the capillary into the interstitium and from the interstitium back into the plasma via lymphatics. Having to know that water moves in and out of each compartment in our body, we need to be more aware of the fluid that we administer to our patients, not just the type of fluid, the volume, as well as the fluid rate that we prescribed. It's all are an act of balance between fluid bolus, maintenance, correction, and not to overdo it until you cause fluid overload or edema. There's a lot of evidence nowadays that showing too much of fluid will cause more morbidity and mortality in sick children. This graph is showing how the percentage of body fluid changes in time. As you can see, at birth, the percentage of water in the body is around 80% and gradually reduces to 60 to 70% during adolescence and adulthood. So how do we know how much fluid does a child need? It is actually extrapolated from the metabolism of normal children, whereby for every first 10 kilogram, the amount of energy spent is 100 cal per kilogram, and second 10 kilogram is 50 cal per kilogram, and subsequent 10 kilogram onwards is 20 cal per kilogram. Since energy end product is water, therefore the calories required per kilogram is converted to the water required per kilogram, and we are still using the same formula till now. This is a guide on how you prescribe fluid in children based on age and weight. Make sure you know how to calculate this, as it is very important to be able to prescribe the amount of fluid you want to administer in children and not to cause problems with fluid overload or undervolume. These are the different types of maintenance fluid that we usually prescribe in pediatric ward. I highlighted the ones in red as we should be using isotonic solution for our patients. For fluid bolus, you can give 10 to 20 ml per kilogram of crystalloid or colloid until the blood pressure stabilizes. And for fluid correction, it depends on the percentage of dehydration over time. For example, if you have a 10 kilogram child with 5% dehydration, you will need to multiply 5% to the body weight, which is 10 kilogram, for every liter, which is 1000 ml. You will get 500 ml over 24 hours. Therefore, you need to write down the drip infusion rate as 20 ml per hour. By now, I hope you understand how important is sodium. Almost all type of fluid we have discussed will have sodium as the main cation. And be aware of hypo and hypernatremia and know in general how to treat them. And not to forget potassium, as the running of a cell depends a lot on potassium. Be aware of hypo and hyperkalemia. Know the complications that may arise with it, and know in general how to treat them. Apart from calculating the total fluid, we also need to think about the amount of calorie we are providing for children, As you know, they need nutrition to grow. In general, the energy requirement for a child is 80 to 120 kcal per kilogram per day. If you want to know whether a baby is growing well with enough nutrition, you can counter check how much the baby is drinking. For example, a 5 months old baby weighing 6 kg is currently taking infant formula of 3 ounces every 3 hours. If you calculate every meal of infant formula gives 0.7 kilocal, you will get the total calorie of 112 kilocal per kilogram per day, which is enough for the baby. And the total fluid the baby is taking is 120 mils per kilogram per day, which is also a good amount to keep the baby hydrated. If the child is more sick and could not tolerate enteral feeding, we have an option of parenteral nutrition. Each macronutrients contribute to the total calories for the child. So my take-home message to you is that, remember, fluid compartments are divided into intracellular and extracellular compartment. Delivery of fluid in children includes bolus, correction, and maintenance. Electrolytes are very important, so please monitor them regularly. Think about the calories as well as apart from the total fluid amount.